This first lecture is about the real numbers, and we can represent the real numbers on a straight line. And we pick a point, a special point, which we call the origin, and we place the number 1 unit to the right of that origin, and the number 2 units to the right, and so on and so forth. So the numbers to the right of our origin are positive numbers, and the numbers to the left are negative numbers. We have all of the natural numbers to the right of the origin. These are the counting numbers, 1, 2, 3, 4, etc. And they're usually denoted by this n. And this says that the set of our counting numbers 1, 2, 3, 4. The integers are a larger set. They include all of the counting numbers, but they also include 0, and they include the negatives of the counting numbers, which lie to the left of the origin on our number line. So to the left we have -1, -2, -3, and so on. Those are the integers, and they're usually denoted by z. An even larger set is the set of rational numbers, and these are the set of all numbers that we can make by dividing a by b, where a and b come out of this set of integers. So some examples of rational numbers here are every counting number is a rational number, because if we divide it by 1, then that gives us the same number. So 2 over 1 equals 2 is a rational number. All of our negative numbers, -3 over 1, -3 is a rational number. We also have things between these whole numbers, fractions such as 1 over 2, 5 over 4, 22 over 7, etc., etc. And this is a bigger set than the whole numbers. It contains all of the fractions between these whole numbers. Now, the real number, the set of real numbers, is even bigger than the set of fractions, or the set of rational numbers. So we give the entire line the name R, and that stands for all of the real numbers. And the ones that are missing out of the rational numbers are the non-rationals or irrational numbers. And you probably already are familiar with some of these. Pi is 1 and the square root of 2 is another. And they cannot be written as fractions of whole numbers. In their decimal point expansion, the decimals go on forever with no repeated pattern. So, and there are not just 2 more, there are many, many more irrational numbers. So the real numbers is much bigger than the set of rational numbers. So this is the order in which the sets lie inside each other. We say A is a subset of B if, well, we write it this way: A is a subset of B if A is a subset of B. And so we have our counting numbers. N is a subset of the whole numbers, which is a subset of the rational numbers, which is a subset of all of the real numbers, which is every possible number on our real line. Now, one very important thing about the real numbers is that they're ordered. And so for every 2 real numbers, A and B, I have either of 3 things: either A equals B, or A is less than B, or B is less than A. And so all of the numbers, because they lie in that straight line, they can all be ordered in a total ordering. So given any 2 points, we can talk about the points between A and B because of this ordering. And so we call the set of points between A and B an interval. And when we're talking about these intervals, it's important to indicate whether we're going to include one or both endpoints or neither of the endpoints in our set. So we have several different types of intervals, and you'll see below we have 3 different ways of describing the intervals or representing them. We also have intervals which extend to plus and minus infinity, and we'll show the notations for each type below. And this mathematical statement, which is the set theoretic description, can be read in the following way. It's the set, the curly brackets mean set, of all real numbers x, so that A is less than or equal to x, which is less than or equal to B. So this is a set of numbers which contains A, and it contains B, and it contains every real number x between A and B. In particular, this vertical line means such that in mathematics. Okay, so we have 3 different ways of describing these intervals. The first case that we might think about is the interval of values of real numbers between A and B, not including either endpoint. And so if we're representing this on our number line, we put dots at A and B, which are hollow, to indicate that neither A nor B are included, and then we shade in the line between A and B to indicate that everything between A and B is included. And in set theoretic description, the set of all points between A and B, not including A or B, is the set of all x such that A is less than x, strictly less than x, which is strictly less than B. And this is our interval notation, which is probably the easiest way to represent this interval. And this means the interval from A to B, and when we're excluding the endpoints, we put these round brackets. Now, when we're including an endpoint, we put a square bracket at that endpoint. So this interval, in interval notation, means the set of all points between A and B, including both endpoints. In set theoretic description, that's the set of all x such that A is less than or equal to x, which is less than or equal to B. And on the number line, we put solid dots at A and B to indicate that A and B are included, and then we shade everything between A and B to indicate that all of that is included in our interval. We might just include one endpoint. Let's say we include B and not A. Then we put a round bracket at A in the interval, in the description of the interval, and a square bracket at B. And this is the set of all x, so that A is strictly less than x, and x is less than or equal to B, so x might be B. And so here we have a hollow point at A to indicate that A is not included, and a solid point at B to indicate that B is included in our interval. And then we shade everything in between A and B to indicate that all of that is included in our set or our interval. And you have a similar situation if you include A but not B. And then we have some intervals that stretch to infinity or minus infinity. So for example, if I want to describe the interval, which is all real numbers which are greater than A, the set of all x so that x is greater than A, then in interval notation, that's the set of all points between A and infinity, and certainly not including infinity, and in this case not including a. And on our number line we put a hollow point, a hollow circle at a, and then we shade the line and we put an arrow at the end of the shading indicating that this shading goes on forever. Similarly, if we want the set of all points x, the set of all real numbers less than or equal to b, then we're looking at the set of all x values between minus infinity and b, and we're allowing b into this set. So in interval notation, it's the set of all x between minus infinity and b, including b, so we have a square bracket of b. And in set theoretic notation, it's the set of all x, so that minus infinity is less than x, which is less than or equal to b. And so now we put a solid dot at b to indicate that that's included. And then we have a line pointing towards negative infinity, indicating that everything all the way down to negative infinity is included. And of course, the interval from minus infinity to infinity is every possible real number. Here we have some examples. If you were asked to sketch the interval from 1 to 3, not including 1 or 3, then your sketch would look like this. You have a hollow point at 1, hollow point at 3, and you're including everything in between. And this set from 1 to 3, not including 1 but including 3, looks like this. Its picture. We don't include 1, so we put a hollow circle at 1 and a solid dot at 3 to indicate that that's in the set, and then we include everything in between. 1 to infinity includes 1 and everything above it, which we indicate by that arrow, and everything less than 3, strictly less than 3, well, 3 is not included, so we put a hollow dot at 3, and then we include everything to the left. Here are some problems to work on yourself. Graph the intervals from 1 to 7, including 1, not including 7. This one 0 to infinity, this one minus infinity to minus 1, and minus 1 to 3. And you can check the answers on the next video.